Okay, so we're going to look at another application of integrals, arc length, which is, as the name implies, finding the length of a curve. Any curve in space, we can use an integral to find its length, particularly for not straight curves, right? We can't just use the distance formula to compute the length if I have a curved, not a line. So to find the total length of a curve, if you can picture some kind of a curve here in the same spirit as we've been doing area, volume, we break it up into small pieces. And each one of those little tiny pieces is a small piece of arc length. We're going to use S for arc length. So ds would represent an infinitely small section of that curve. If you zoom in on that little section, even though it's curved here, at a microscopic level, this would represent a right triangle where you can think of ds as that little arc length, and you could think of dx as how far from here to here, how far do you move in the x direction, how far do you move in the y direction. So ds has sort of a small x change and a small y change associated with it. And we've gotten used to describing small changes in x as dx, small changes in y as dy. Now, since this resembles a right triangle, the Pythagorean theorem would say that a hypotenuse squared would equal dx squared plus dy squared, which means ds itself would be the square root of dx squared plus dy squared. If I take this and divide everybody by dx, so I have ds dx, if I put a dx in here before I square it, and same thing here, dx over dx is just 1. So this turns into a 1 dy dx squared. And then if I integrate dx, ds dx to get a formula for s, for the total arc length, it would be the integral from some number a to some number b, that would be given, of the square root of 1 plus dy dx squared times dx. So let's look at an example for that. We want to find the arc length, the length of the curve, y equals x to the 3/2 from 0, 0 to 4, 8. The formula involves taking the derivative and squaring it. So I did that off to the side here. The derivative of x to the 3/2 is 3/2 x to the 1/2. If I square it, that will become 9/4, and x to the 1/2 squared is just x. My formula will be in terms of x, so I would be integrating from x equals 0 to x equals 4. That's why my limits are 0 to 4. Square root of 1 plus dy dx squared, which is just going to be 1 plus 9/4 x. This is a great time to use a u substitution. If I let u equal 1 plus 9/4 x, du is 9/4 dx. All I have is a dx left over, so I need to wish for a 9/4 so that this could be converted to a du, and I'll compensate with the reciprocal outside, 4/9. So then in terms of u's and du's, 9/4 dx just becomes du. This is u to the 1/2. The 4/9 stays outside. I chose not to change my limits. Remember, we talked about that in a previous video. You can convert your limits in terms of u if you want to. I chose not to here. My antiderivative is 2/3 u to the 3/2. I put my u back in, and now since I'm back in terms of x, I can use my original limits from 4 to 0. I just multiplied these together, so I have 8/27. If I plug in 4, that will cancel here. I'll have 1 plus 9, which is 10 to the 3/2. If I plug in 0, I'll have 1 to the 3/2, and 1 to any power is just going to be 1. One more example for arc length, and there's a fair number of these types of arc length problems in our book. It seems like a very random, weird looking function, and there's a reason for that, okay? So So we want the length of this function from x equals 1 to 2. Knowing that it's going to take some work to find the derivative and square it, I just did that right off the bat. So I rewrote this as 1/4 x to the 4th. I brought this x to the second up to the top, so it's x to the -2. That makes taking my derivative easy. X cubed, if I bring down the 2, -2/8 reduces to -1/4, x to the -3. And then you can rewrite this if you want to. I brought the x to the 3rd down with the 4. So I get x cubed minus 1/4x cubed. My formula involves squaring that. So if I multiply it by itself, x cubed times x cubed is x to the 6th. Notice what happens with my middle terms here, right? If I have x cubed times -1/4x cubed, the x cubes will cancel. I'll just be left with -1/4. Same thing for these two. And then this times itself will be positive 1/16 x to the 6th. And then you can combine these two -1/4 to make that x to the 6th minus 1/2 plus 1/16 x to the 6th. Now if I plug that into my formula for arc length, 1 plus square root of 1 plus dy dx squared, 1 plus, and here was what I got for dy dx squared. Now here's the key to figuring out this problem. I'm going to take this 1 minus 1/2 and make that positive 1/2, and I'm going to put it in the middle. I could, in theory, I could put it wherever I want, but I'm going to put it there because what you're supposed to notice here is this result looks an awful lot like what we got here, right? Except this was minus. And where did that come from? That came from squaring this, right? That came from squaring x cubed minus 1/4x cubed. So it stands to reason then that x to the 6th plus 1/2 plus 1/16 x to the 6th must be what you get when you square x cubed plus 1/4x cubed. So you have to recognize that this is really that squared. That's the key to the whole problem, because the square root of this squared just cancels it out, leaving me with the inside. I brought up the x to the 3rd so I could integrate it. X to the 4th over 4, leave the 1/4 there, raise that up by 1, x to the -2 over -2. And then I just rewrote this. I brought the x squared back down. And then I plugged in from 2 to 1, do the algebra, and I got 3 and 27/32 as the arc length. So a lot of the problems, be careful when you do these, you really got to look for a perfect square. That's the key. You're looking for a perfect square on one like this.